This is another example of an open interval problem, but we'll still be able to solve it using our normal optimization methods. So what's the smallest amount of metal I can use to make a cylindrical can that contains 1 liter of volume, which is 1,000 cubic centimeters? So geometry again, let's draw a picture. And what are we trying to deal with here? So we have a radius and a height for this can, and I'm told the volume needs to be 1,000 cubic centimeters. What am I trying to optimize here? I want to use the smallest amount of metal, which means I want the shell to be as small as possible. I want to minimize surface area. Well, what's the surface area here? Well, it's going to be the two faces, the top face and the bottom face, which is 2 times pi r squared, and then the lateral face, which is a 2 pi r h. How am I going to get this down to one variable? I'm going to use the volume. The volume of a cylinder is pi r squared times h. So we know that 1,000 equals pi r squared times h, or that h is 1,000 over pi r squared. I can take that and plug that in here to simplify my equation. So my surface area as a function of r is going to be 2 pi r squared plus 2 pi r times 1,000 over pi r squared. Simplifying this out, 2 pi r squared plus 2,000 over r. Now, where am I allowed to take r? What values of r are valid for this problem? Well, this can could be as tall and skinny or as short and wide as I want. So I'm allowed to take r being any value between 0 and infinity. So it's an open interval problem. I can't really plug in the endpoints here because they're not defined. However, as r gets really close to 0, this term blows up because I'm saying 2,000 over r. As r gets really small, that gets really big. On the other hand, as r goes to infinity, this term gets really big. So near both endpoints, my surface area gets really, really big, which means that's not where the minimum is going to occur, because I'm trying to minimize surface area here. At the two endpoints, it gets really, really big. Like, ignore those and just focus on any critical points that are inside and use those to determine if things are maxes or mins. Let's now hunt for a critical point somewhere inside. Let's take a derivative. I get 4 pi r minus 2,000 over r squared. I want this to be equal to 0, and I can solve this out. 4 pi r equals 2,000 over r squared. Tells me that r cubed is 2,000 over 4 pi, which is 500 over pi. And since there's only one positive real number with that as its cube root, it means I only have one critical point inside. And that's at r equals the cube root of 500 over pi. Now, we could argue the argument that since both endpoints go off to infinity, this must be a minimum. Or we could build a number line for the derivative surface area and see that at my point here, I have a minus here and a plus here, which means that point must be a local minimum. And since it's the only critical point, it must be the only minimum that you have. Therefore, this has to be the minimum here. So that's another example of an open interval problem that involves optimization and how you can argue that the point you get is actually where the minimum occurs for this problem.